Namaste. We are Team Shunya of Triple ITDM Kanchipuram, India, and we are proud to present Lakshya, the fifth rover of our journey. Since April 2020, our team has been focused on exploring and accumulating scientific and technological knowledge in space and robotic technologies by developing unique viewpoints and innovative solutions. To ensure streamlined workflow, our team is structured for both strategic and technical efficiency. At the top, we have a team lead who derives overall mission and strategy supported by a technical lead for technical direction and system integration. For internal operations, our team is organized into five specialized subsystems: mechanical, electronics, software, science, and management, each guided by dedicated team leads. Over the past few years, we have been actively participating in many prestigious rover competitions, such as IRC conducted by Aspiros and IROC conducted by ISRO, consistently delivering strong results and improving our overall performances. Building on this foundation, we now aspire to take our next step and represent our country as well as our college at European Rover Challenge 2025.
In Rohar Lakshya, we have implemented four-wheel drive with independent steer. This year, we have made several improvements keeping in mind the failure points seen in our previous designs. The rover mobility system is designed to provide smooth and stable drive over rough and challenging terrain. How do we achieve this? Starting from the ground, we have created the wheel using TPU and PETG support for keeping the weight as minimum as possible. We have added the airless wheel design in our wheels, which helps to increase traction, reduce vibration, and it also helps in absorbing impacts, which results in stable drive over challenging terrain.
We have manufactured lightweight wheel mounts with aluminum material, which provide good strength to weight ratio. The rocker suspension is used to maintain the rover stability on uneven ground by distributing the weight equally, while the differential bar helps in maintaining contact with the ground. 20 mm mild steel square pipes are used for the structural frame of the chassis, which enables it to withstand the torque when the manipulator is completely stretched out.
The electronics of the rover deals with power distribution, controls, and communication. The rover uses ESP32 dev kit for its better processing power and multiple built-in communication protocols like Wi-Fi and Bluetooth, an upgrade over the STM32 which we used earlier. ESP32 controls the gear DC motors for drive and steering, which are equipped with encoders to achieve velocity control for drive and position control for the steering, using PID control algorithm. The spot-on mechanism using four-wheel steer facilitates easy autonomous control while applying less stress mechanically. The drive and the steering mechanisms are powered by 18-volt supply and 12-volt supply respectively. The whole rover consumes around 750 watts of power.
Two custom-made PCBs have been developed to distribute power, secure connectivity between components, and ensure modularity. These are fitted with fuses for overcurrent protection and a relay-based kill switch to cut off the rover's power supply under unsuitable conditions. The omnidirectional ubiquity rocket setup, operating around the 5 GHz band, acts as the rover's primary source of communication because of its high bandwidth. If it fails, the secondary communication is the long-range LoRa module, which transfers important information until primary communication is re-established. It can also act as a remote kill switch. We have shifted to roster to interlink different software capabilities and electronic components. The rover is controlled through a joystick during teleoperation. The control system of the rover receives commands from the onboard computing unit, Jetson Orin, using microROS.
For rover's mobility, we use a set of core sensors, IMU for orientation, wheel encoder for odometry, and a 2D lidar for scanning the environment. These data streams are then published as topics IMU, ODOM, and SCAN, which are then fused using an extended Kalman filter, which helps us in estimating our rover's course. For autonomous acceleration, we use RTAB map to build a real-time map of the environment. This map is integrated into the Rosto navigation stack, which handles both global and local path planning. The system dynamically updates course maps, avoid obstacles, and plans efficient routes using planners like DWB or TEB. This entire setup enables the rover to navigate safely and adapt to unknown environments without manual intervention.
Here you can see our rover making its way through the terrain, spotting an Aruko marker ahead. It's using real-time camera data to understand its surroundings and figure out exactly where it is. This visual data directly assists in navigation, manipulation, and task-specific decision-making across both the rover and drone.
Alongside the rover, we have developed an autonomous drone system for aerial tasks. The drone utilizes PX4 flight stack integrated with ROS2 through Mavros. This lets us control the drone in both manual and autonomous mode via onboard commands. The above-mentioned things have been successfully implemented in a commercial off-the-shelf drone.
For real-time positioning, we rely on onboard IMU and barometer data. Along with this, we have visual odometry or optional GPS, depending on the environment. Using Mavros topics, we send trajectory waypoints or velocity commands to guide the drone through tasks like aerial mapping or inspection. There are several safety mechanisms like monitoring the telemetry, geofencing, and fail-safe triggers that are built to ensure robust operation during the mission.
From the mechanical surface system, we currently have a 5-degree freedom manipulator, which is made up of aluminum 606 wrap and PETZ, which is capable of picking and placing object up to 5 kilograms. At Link 1 and Link 2, we are currently using linear actuator, which is capable of applying force up to 1000 Newton, and its stroke length is 10 centimeter.
Currently, we are operating the base link using a 140 kgcm motor with torque optimization using spur gear of Module 3. At Link 3, we currently have a bevel gear differential mechanism for controlling the up and down and rotational motion of the end effector. For future, we will be using a cycloidal gearbox at the base link, which outputs a very high torque while the space occupied is minimized. For the Link 3, we will be implementing the mechanism using a coaxial shaft, which results in high effective torque transmission while being compact.
To interact with the environment just like our hand, we use Robotica mounted on the rover. It's controlled using Movit for motion planning and allowing us to perform precise pick and place and various tool operations.
Of our science caching system. So basically we have these two containers which help in the storage of the rock samples that will be collected, and then we have the manipulator which would help us in obtaining these rock samples, and there would be a clearance of up to 15 centimeters in width. And now we have this complex gear system which enables our drill to dig up to 30 centimeters in depth. And next up we have a sliding box mechanism which enables us to collect the soil from the drill after it's been collected. This would be mostly used for the regolith and the deep sample. Here is the region allotted to us this year, the Valles Marineris. So this year our team has opted to go with Google Earth Pro for its needs, as it is more easy to use and is well sophisticated to our needs. And as per the guidelines, we have access to various layering options of the surface, and also we have the high rise and prism imagery of the surface. This enables us for precise site selection and better path planning for our rover.